Hello everybody, I hope you can hear me and see me. Um, this is the Linear Algebra review session. Thanks for coming. Nice to see you all, see some of you, see your names. It's a shame we can't be together to do this, but we'll get by all right. I am going to record this and put it on YouTube, which is what I've been doing with all of my classes this semester. So maybe I will, Kaylin, if I send you the link to this, can you send it out to everybody? Kaylin?
Yeah, no problem.
Okay, great. So hopefully, you know, if people couldn't make it, they can, you know, see it that way. And you can watch it again if you want. Be sure to like and subscribe. Yeah, so I have a bunch of stuff that I can just go through, but I want to have like I can take questions too. I don't know how you all wanted to do this. Do you guys have like specific questions that you want to go over, or would you rather me just kind of say a bunch of stuff? Anybody have an opinion? Say a bunch of stuff. Okay.
Yeah.
Yeah. So I can try to give you like the 1 hour version of a semester of linear algebra, and then you know, if you do have questions or you if something I say you want to talk more about, feel free to interrupt, or you know, at the end we can go back and talk about anything that you feel like I left out, or maybe just want more details on. All right. I'm not, you know, it's not really possible to hit everything in an hour, but I'll do my best, and then we can try and fill in the blanks after the fact if you want. Sound all right? Yes. Okay, let's do it. So let's start with, how about solving linear systems? This is the sort of basic thing that linear algebra grew out of, and a lot of the stuff we do in linear algebra is based on the basic concept of solving a system of linear equations. So here is an example. 2x plus 7y minus z equals -2. 2x plus y minus 8z equals 18. All right, this is a system of linear equations. And the general idea is you want to solve the system. What that means is find values for each of the three variables to make all the equations true. You could think of this geometrically also. This would represent, each one of those equations represents a plane in R3, and solving the system would correspond to finding an intersection point of all three planes. And generally you would expect them to intersect in a point, although in some special cases they might not intersect at all, or they might, you know, all intersect in a line or something like that. Anyway, the way to figure this out is by putting these in a matrix and then doing the Gaussian elimination, or the Gauss-Jordan elimination. So I'm going to make an augmented matrix. This is something I hope you remember how to do. Right? I put the coefficients in the matrix like that. To the left of the bar are the coefficients in front of the variables, and then to the right of the bar kind of represents the position of the equal sign. And to solve the system, you want to do what we call the elementary matrix operations, and these are not so hard to do, but you got to remember how to do it. So they involve adding rows to one another in order to cancel things out. And what I'm looking for eventually is called the reduced row echelon form, which ideally will look something like this. Now this is not always possible, as you recall, but that's sort of what I'm aiming for. So the idea is, first of all, I want to put a 1 in the upper left corner, which, lucky for us, there already is a 1 right there. And I'm going to do row operations to put zeros below the 1. So the first operation I'm going to do is subtract 2 times the top row from the middle row. And I'm going to leave the top row like it is. subtract 2 times the top row from the middle row. This is going to be a 0. Anybody want to shout out, what am I going to get in the next position over? You've got to shout it. I'm subtracting 2 times the top row from the middle row. 1. Yeah, I think maybe -1. If I'm doing this right, it should be 7 minus 2 times 4, right?
Yeah.
So it shall be -1, I think. I hope everybody got something like that and you just didn't want to shout. That's all right. Then in the next position, it's a -1, and I'm subtracting 2 times the top row. So it will be -1 minus 2 times -2. I guess that's -1 plus 4, which is 3, right? And then on the far side of the bar, I get 2 minus 2 times 4, 2 minus 8, which is -6. All right? Is that right? 2 minus...
Isn't it -2 on that side from before?
Oh, did I? Yeah, thank you. I'm looking at my paper and I realized it was off. Yeah, I just copied this number wrong. Sorry about that. Thank you, whoever said that. And then, so over here it's not -6. It's -2 minus 8. -10, right? Yes. Now, when it comes to the comprehensive exam, you should do this on your calculator. So if you don't know how, you should figure out how by then. There is a you can use your calculator on the comprehensive exam, and if you have a a TI graphing calculator, there are functions in there to do matrices, and in particular they can do this row reducing operation. So you should learn how to do that. And when it comes to the comp, you should not try to do this by hand. But I wanted to do just one example, just so that we all remember how to do it. Okay, I'm going to do the same procedure on the bottom row. So I am going to, again, it's the same operation, this time with the goal of putting a 0 in this position. So I'm going to subtract 2 times the top row from the bottom row. That gives me a 0 here. Next is going to be 9 minus 8, which is 1. Next is going to be -8 minus -4, which is -4. And then on the far side, I'm going to have 18 minus 8, which is 10. All right? This is how we do these are called the elementary row operations. The next thing I would do is, because this is the format, remember, that I'm looking for as my final answer, or at least something as close to that as we can get, the next thing I'm going to do is to make this +1 in the middle position here. Anybody remember how to do that? What's the operation I should do to make a +1 in this position? Anybody remember? There are 3 types of row operations you're allowed to do. You can add a multiple of one row to another. You can multiply a row through by a constant, a non-zero constant, or you can do a row exchange. I almost never do row exchanges. It's almost never necessary. I would, in order to make this a +1, I would multiply through this row by a constant, in particular by -1. It will switch that to a +1. So the next step would say 1, 4, minus 2, 4, 0, 1, minus 3, 10, like so, right? I multiplied through the middle row by -1. Okay, let's continue. I'm going to, now, my goal in the next step is to put 0 in this position where the 4 is, and also put a 0 in this position where the 1 is. So I'm sort of using this 1 in the middle, and I'm going to do eliminations upwards and below to put zeros in those other 2 positions. So I'm going to copy the middle row like it is, and then to get a 0 above the 1 in the middle, I'm going to subtract 4 times the middle row from the top row. It leaves a 1 here. I get a 0 here. The top row minus 4 times the middle row. That should be negative 2 minus 4 times negative 3. That's negative 2 plus 12, which is it 4 times the middle row? I'm trying to look on my paper. On my paper I said 10 here. 4 times the middle row. Yeah, subtracting from the top row. Negative 2 minus negative 12 is 10, right? I think so. This, as you all know, if you've been in my class before, I'm not all that good at adding and multiplying numbers together. I'm also not very good at pushing buttons on a calculator, so either way, I mess it up. And then on the upper right corner, we have 4 minus 4 times 10. 4 minus 40 is negative 36, right? All right, I'm getting a little tired of this. Would you mind if I just wrote down what I wrote on my paper? This is what the bottom row is going to be. Now, on the test, you're going to do this with your calculator most of the time. It is important that you understand how to do the procedure by hand, because sometimes you need to think it through. But would you mind if I skip a few steps and just jump to the end here? When you do this on your calculator, it will spit out what is called the reduced row echelon form, which in this case, well, we know the first row is going to look like that. Here's what I got when I did this. All right. Anybody remember, how do we read out the answer here? Remember, the answer was supposed to consist of specific values for x, y, and z. What's the answer going to be?
X equals negative 36 and y equals 10.
Yes. And z?
Equals 0.
0. Yeah, great. This matrix now, if you read the rows across, the top row says 1x plus 0y plus 0z equals negative 36. So x is negative 36. The middle row says 0x plus 1y plus 0z is 10, and so on. You get the idea. The point of the row operations is doing the elementary row operations does not change the set of solutions, which is why you can do all these operations and then you read the answer very easily at the end. All right, this is the Gaussian elimination, or the Gauss-Jordan elimination procedure. Any questions about that one? This is a procedure. You should understand how to do it by hand, but in practice you can do it on your calculator on the test. Let's just look at one other. How about this? X plus y equals 2. This is just 2 variables. Minus x minus y equals minus 2. So this is an example where you don't get that nice form that we got at the end last time. Anyway, you put this in a matrix. In this case, you get 1, 1, 2 across the top, and then minus 1, minus 1, minus 2 across the bottom. You do some elimination steps. I already have a 1 in the upper left corner, which I like, so I'm going to try to eliminate below that 1. I'm just going to add the top row into the second row. So up top, I still have 1, 1, and 2. And then I add into the second row. I'm going to get 0, 0, 0. Zeros all the way across, all right? Now, these things, there's some basic terminology here. These ones in the first row, sorry, in the first non-zero entry of each row is supposed to be a 1. Once you're done with the elimination, the first non-zero entry in each row will be a 1. If it's not, then you didn't do it fully. In this case, I have only one of those. Those are called the pivots, or they're sometimes called the leading ones. All right. What do we do to write the solutions in a case when we don't have a pivot in the second row here? There's a little procedure that you do to write the solutions of the system using parameters, or sometimes called free variables. And the rule to do this is something that you just, it's a little obscure in other classes, but you might want to refresh your memory about how you do this. Each column without a pivot, or a leading one, becomes a parameter, or a free variable. People use different terminology for this. We'll call it a free variable. All right? And so in this example, this column here is going to be a free variable. I'll call it t. I don't know what your linear algebra book tends to call it. So that column is going to be t. So these columns, remember, the first one represents the variable x, and the second represents the variable y from my original system. Right? And so the fact that that second column is my parameter t, that means I'm going to say y equals t. And then I write out the first row. So row 1 says now x plus y equals 2. But if you write that in terms of the parameter, that would say x plus t equals 2. And I can solve this for x in terms of that parameter. X is 2 minus t. All right. And now we can write the set of solutions in terms of this parameter. So my solutions are, maybe I'll write it as a vector, x, y equals 2 minus t and t. So what you see here is there are infinitely many solutions. That is, you get a different solution for every possible choice of t, and t can be any real number here. So we have infinitely many different solutions. And in fact, you can say geometrically what this looks like. There's another little trick that you probably did in your linear algebra class about, you can sort of separate this out. I can say this is 2, 0 plus minus t. Separate out the parameter from the constants. And then this you can also further separate or simplify or something. Factor out this t, right? And what is that? Well, this expression that I got at the end, you can say that represents a line in R2. In fact, it is a line in R2. You can say actually very specifically what it is. It's a line through the point 0, 2, which is here, in the direction, so this is a point on the line, and this here gives you the direction of the line. So it is a line through the point, sorry, it's not 0, 2, it's 2, 0. I wrote the wrong point. 2, 0, that's over here. X equals 2, y equals 0. And it has the direction of that other vector, which is x equal minus 1, y equal 1. So it's like this, right? That's that other vector. So the set of solutions is that line. All right. So this is what it can look like when you don't get a specific solution. You might have to do this slightly weird parameters, free variables thing. All right. Any thoughts about that one? Questions about that one? I hope this looks familiar. My goal is just to kind of jog your memory. Hopefully everything I say will sound familiar once I say it, although you may have forgotten how to do a lot of this stuff. All right, great. Let's move it on. Okay, there's a relationship between these systems and a yeah, I might as well say this, but I don't have much to say about it right now. But anyway, another way to think of this system, this is equivalent to a matrix and vector equation that looks like AX equal B. So from one point of view, linear algebra is all about solving linear systems, but really most of the class you don't think about linear systems per se. You do very often think of matrix and vector equations like this, where A is a matrix, X is a vector of variables, and B is a vector of constants. And this system here is equivalent to this matrix equation, 1, 1, minus 1, minus 1, times the vector xy equals the vector 2, minus 2. And so anything you can say about solving systems is really equivalent in some way to saying something about solving equations of a matrix times a vector, where you have a constant matrix times a variable, a vector of variables equals another constant vector on the right side. All right. Okay, let's talk about linear combinations and linear dependence and independence. This is a major topic. Let's say something about this. How about linear combinations and independence? All right. The concept of a linear combination is not a hard idea. A linear combination of two vectors is just any kind of sum with constant coefficients. So a linear combination of vectors is a sum with constant coefficients. Like something like, 5 times 1, 2, 0 plus -2 times 3, 0, 1. This is called a linear combination of those two vectors. You're just adding them together with constants in front. And of course, they do add up to something. You can multiply this out if you want to. This one adds up to -1, 10, and 2. All right? And what I just wrote, a linear combination of vectors, this can also be rewritten as a matrix equation. This one would take this form, 3, 0, 1 times the vector 5, -2 equals -1, 10, and 2. So linear combinations also can be written like matrix and vector equations, which means, again, like writing linear combinations is somehow like on some deep level related to linear systems of linear equations. All right, and we're going to talk this, of course, this multiplication operation being used right here is a weird matrix multiplication operation, which you definitely need to refresh your memory about if you haven't done it in a while. And I'll talk in more detail about that in a few moments. Oh no! What? It's okay. Something weird just happened with my screen. I've been having trouble with my my screen lately. All right, sorry about that. Hopefully it won't happen anymore. Okay, so this is about linear combinations. A big word that you need to remember is the span. The span of vectors is the set of all linear combinations of those vectors. Of those vectors is what I'm trying to write. That's called the span. So it's a very common question to see. I give you some vectors. I say, is this vector part of the span of these other vectors? Let's try to do one like that. So here's a question. Is this vector 4, -2, 18 in the span of these vectors? 1, 2, 2, 4, 7, 9, and -2, -1, -8. Is that one in the span of these other three? What it means is it possible to write the one on the left as some linear combination of those other three? Can I add those three together with constants in front and make it add up to the thing on the left? All right. I suppose you could try to like guess the answer to this, but you don't want to rely on that. How would we set this one up? The question really is, we want to find, can we find constants, I'll call them C1, C2, C3, with the, something like C1 times the first one, plus C2 times the second one, plus C3 times the third one. Can we actually make them add up to this one? Right? That's the question. Can we find constants that make this happen? And as usual, like your goal in many, many linear algebra problems, your sort of first order of business is, how do I turn this into a Gaussian elimination question? And then you push the button on your calculator. That's like the way that you solve many of these questions. So how does this question relate to a Gaussian elimination? Well, this can be rewritten as a matrix and a vector equation. So this is the same as this, if you write those three vectors on the left as columns times these guys as variables, and it equals 4, minus 2, and 18. All right? Those are the same, just because they are. I don't know if I want to explain. I mean, it has to do with the somewhat weird way in which you multiply this matrix times this vector, which I said I'm going to talk a bit about later on. But that being the same as that means it's the same as solving this matrix equation. 1, 4, negative 2 with the bar and the 4. 2, 7, minus 1, negative 2. 2, 9, minus 8, and 18, right? And that you can just do the elimination on your calculator and see if we get, if we can find those C's or not. What happens when you do the elimination? So here I do the elimination. I'm just going to tell you the answer. Type this into your calculator. What you get, actually this, you don't have to type this into your calculator. That, I cooked this up. This is the same matrix that I did by hand in the first, the first 5 minutes. It's the same matrix. So you get this, minus 36, 10, and 0. All right? Sorry, that's under my beautiful face. Like that, okay? And so, what is the answer to my original question? My original question was, is this in the span of these other ones? What do you say? I mean, it's a yes or no question. I see some people nodding. I see one person nodding. The answer is yes, it is in the span, because I did get values for the C's. So I can say C1 is negative 36, C2 is 10, C3 is 0. So yes, it is in the span. And in fact, I can tell you what the constants are, and you can check your answer if you're unsure. You can just verify that when you use those numbers, they actually do add up to the thing that they're supposed to add up to. All right? So yes, it is in the span. How could you ever get a no in a problem like this? There are some cases when you do the elimination and you end up concluding that there is no solution. That would look like if you ended up with something like this, something like that. This bottom line here would indicate no solution. And this is what it would look like in a problem where you ended up saying no, it's not in the span. You would have gotten, your matrix would have ended up something like that, which if you read this row across as an equation again, it says 0x plus 0y plus 0z equals 2, which is impossible. And this is why it has no solutions. All right, how we doing so far? All right, I hope I'm not going too fast or too slow or what. Okay, I hope there is some kind of geometric interpretation of what the span means. The span is taking all possible combinations of a set of vectors. So generally speaking, the span of one vector is geometrically a line, right? If I have just one vector and I ask you, what are all the other vectors I can get by like adding this vector to itself with various constants in front? The answer is all the vectors you can get by adding this one vector to itself would just be any other vector in that direction. So the span of one single vector will be the entire line which contains that vector. Unless that vector is the zero vector, in which case you don't get a line. You get just the zero vector. You can't get a whole line from just the zero vector. What is the span of two vectors? What's the shape that you get if you have, say, two vectors and you look at all possible ways that you could add those two vectors together? Somebody want to shout it out? What shape will you get?
A plane. Yeah,
generally speaking, you will get a plane. Unless they happen to be in the same line already, then all you get is a line. So the span of two vectors is, I will say, typically a plane. It is the plane which contains those two vectors, you know, like it's sort of like this this is going to look like nothing, but it's like this plane here, which goes through those two vectors. All right. How do you like that picture? The span of two vectors is typically a plane. Like I said, unless they happen to already be in the same line, in which case you don't get a whole plane, you just get the line. The span of three vectors, generally speaking, will be a three-dimensional space. Again, unless those vectors already happen to be all in the same line or all in the same plane, in which case you just get the same line or the same plane. All of this thinking is what led to the concept of linear independence. So vectors are dependent when they sort of, it's hard to say informally what I mean, but when they are, I'm going to say something like collinear or coplanar or whatever in some other dimension. Dependent means like maybe you have two vectors but they already lie in the same line, or maybe you have three vectors but they all lie in the same plane. That's called linearly dependent. And the reason it's called dependent is because in such a situation you can actually make one as a combination of the others, as a linear combination of the others. Anyway, independent is the opposite of that. Independent is the opposite. That is to say, maybe you have two vectors and they do not lie in the same line, or three vectors and they do not all lie in the same plane, and so on. All right. When it comes down to actually calculating these, like I give you some vectors and you have to tell me if they're dependent or independent, this is definitely something you want to know how to do. The definition that's most convenient to use is for dependent. So I'll write this as a definition. So vectors, I'll call them v1 up to vn, are dependent, linearly dependent, when it means that I'll just write it down. The definition is weird. I hope you remember it. There exist constants, C1 up to Cn, not all 0, such that C1 V1 plus blah, 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 plus Cn Vn equals 0. All right. Your interpretation of this is a complicated definition, but the way to think about this is dependent means it is possible to add the vectors up and make them all cancel each other out. That's how you get 0 at the end, by putting some constants in front. It is possible to make them all cancel out. For example, if you have two vectors which lie in the same line, then if you choose the constant right, you can add them together to make them cancel each other out. Whereas if you have two vectors and they both lie in a plane but not in the same line, there's no way to make them cancel each other out because they're in two different directions. All right. So anyway, this is dependent. Independent then would be the opposite of this. So I'll write that also. Independent means that if you get 0 here, C1 V1 plus blah 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 Cn Vn, if this actually adds up to 0, then all Ci must be 0. All right, and this is actually easy to check. It looks like a complicated definition. It is kind of complicated to hold in your mind, but it's actually pretty easy to check. If I give you some vectors and I ask you, are they dependent or independent? You can verify this very easily. So, for example, here's an example. Are these independent or dependent? 1, 2, 2, 4, 7, 9, minus 2, minus 1, minus 8. Are these dependent or independent? Are they dependent or independent? We're just going to check. We set up a linear combination like this, adding them all up to 0. And then we have to check if those constants, do they have to all be 0 or can they be something else? So we set up a linear combination, C1, 1, 3, 2, plus C2, 4, 7, 9, plus C3, minus 2, minus 1, minus 8. You set up this linear combination, all adding up to 0. And then the question is, are all the CIs, really what I mean is, must all the CIs be 0? This is the question. But we can answer that just by doing a matrix elimination, right? This linear combination adding up to 0 is the same as this matrix. 1, 2, 2, 4, 7, 9, minus 2, minus 1, minus 8, with zeros on the right side. Zeros on the right side because it's all adding up to the 0 vector. And then I can do my elimination as usual. I did this on my calculator. I got like this. So C1 equals 0, C2 equals 0, C3 equals 0. So as far as the question, must all the CIs be 0? The answer is yes. All the CIs must be 0, which means it is independent. That's what independent means. So all CIs are 0. So it's independent. All right. The only other conclusion that could happen is you get some parameters or free variables here. If you get a free variable, that means it does not all have to be 0, because that free variable, like the t or whatever, it can be any real number, so they don't all have to be 0. If you get a free variable here, you say they're dependent. If not, they are independent. All right? This is dependence and independence. Any thoughts about that? Yes. Okay, great. I got another one here I'm going to skip over just because we don't have too much time left. Okay, let's talk about matrix matrix multiplication. We should at least refresh everybody's memory. How about matrix algebra a little bit? That is, it is possible to add and multiply matrices together, right? Matrix adding is not very interesting. You just add, you can add two matrices which have the same size, and you just add the entries in each corresponding position. Also, you can multiply a matrix by a scalar, constant. You just copy that constant onto every entry of the matrix. Matrix multiplication is more interesting. We can multiply, the sizes have to match up. So to multiply, it must be something like m by, it must be something like m by n times another n by k. When you try to multiply two matrices, the number of columns of the first one has to equal the number of rows in the second one. And anyone remember what will the dimensions of the answer be in this case?
M by K.
Yeah, it'll be m by k. You get sort of the, so the two sort of inner numbers have to match, and then those kind of disappear, and the dimensions of the answer are the two outer numbers. Let's just try an example. See if you remember how to do this. What if I have, say, 1, 2, 3, 4, this being a 2 by 2, and then I'm going to try and multiply it by, how about 6, 0, 1, minus 1, 2, 8, right? This is a 2 by 3. I always write rows first and then columns. Okay, first of all, is it even legal to multiply these together? The answer is yes, because this 2 matches with this 2, right? Those two numbers need to be the same. I drew a big dot. I didn't really mean to, just trying to scribble around, right? Those two numbers have to be the same. They are, so it is legal to multiply them, and the size of the answer will be 2 by 3, these two sort of outer numbers. So the answer here will be another 2 by 3. And what is it? I hope you remember how to do this. You know, if we were in a classroom, I would show you with my fingers. You got to sort of use your two fingers. Your left finger should go across the top row here, and your right finger should go down the first column. And to get in the answer over here, to get the row 1, column 1 answer, I go across the first row and down the first column. and I multiply and add as I go. So as I go in this entry, I do 1 times 6 plus 2 times negative 1. I hope you can see that in your mind. 6 plus negative 2, that's 4 here, all right? The next entry moving over to the right is the first row, second column. So I go across the first row of the left matrix and down the second column of the right matrix. I get 0 times 1 plus 2 times 2, which is another 4, all right? Continuing to the right, I'm on the first row, third column, so I go across the first row, down the third column. I get 1 times 1 plus 2 times 8, 17. All right, and so on. I hope you remember how to do this. On the bottom row, I'm looking at the second row in the first column. That means I go across the second row in the first matrix, down the first column. I go 6 times 3 is 18, minus 4 is 14. Next position, I go 3 times 0, and 4 times 2 is 8. And then finally, I go 3 times 8, and 4 times 8, 3 times 1 and 4 times 8, that's 35, right? I think so. This is how we do matrix multiplication, all right? I hope you remember how to do that. It's important. This operation is associative and it is distributive, but it's not commutative. I hope you remember that. If you change the order around in a matrix multiplication, like A times B is not necessarily the same as B times A. Sometimes it doesn't even work at all. Like the sizes might not even match up. But even if they do match up the sizes, it is not a commutative operation. All right. The matrix multiplication operation has an identity element. So actually it is a fact. Now that you all have taken abstract algebra, I can use such words with you. I can say that matrices with their operation of multiplication, they form, well, matrices with addition make a group because you can add 2 matrices and get another matrix. And that operation has a zero, an identity, an additive identity is the 0 matrix. And also it has additive inverses, that is, you can just like subtract. If you're talking about multiplication, the matrices do not quite form a group under multiplication because not every matrix is invertible. There is an identity element for matrix multiplication. It's called the identity matrix, and it looks like this. It's familiar. It has zeros in all other positions, but ones on the diagonal going down like that. This is the identity matrix. I'm sure everybody remembers. Matrices sometimes have inverses. There is a procedure for finding the inverse of a matrix, which is also based on Gaussian elimination, but we write them like this, A inverse, and it must satisfy A times A inverse is the identity, and is also equal to A inverse times A, right? This is the same as from like in a group. This is what an inverse means in a group. And I will just say this is only possible when A is square, that is, it has the dimensions, the same number of rows as columns. That's the only way that it's even possible. And even so, some square matrices do not have an inverse. But the inverses are only possible when the matrix has the same number of rows and columns. And there's a procedure for finding the inverse, which I think is, I've always thought this was kind of cute, the way that you can do this using elimination to find the inverse of a matrix. Let's try, how about this one? I'm just going to do this for a 2 by 2 matrix. All right, let's find A inverse. The way that you do this using matrix elimination is you make a giant augmented matrix where you stick the original matrix on the left and the identity matrix on the right, and you do the elimination with this. And by some kind of magic, mathemagic, when you finish the elimination, you again are going to get, 2 matrices sort of side by side. Because you did the elimination properly, what you see on the left of the bar will be the identity matrix. And what you see on the right of the bar will be some other stuff, and that other stuff is the inverse. So in this example, it ends up being this. 2 minus 1 minus 3, 2. And it turns out, so you put A here. If you do it correctly, what ends up here is going to be A inverse. Right? And if you do this and you don't get, of course this is the identity, right? And this is the identity. If you don't get, trying to write nicely, if you don't get I here, I mean, it can happen sometimes when you do the elimination, something weird happens and you don't get the identity matrix. Too much cancellation or not enough cancellation. If you don't get I here, then it means A is not invertible. Like I said, not all matrices have an inverse. And the way you can tell, actually, there isn't much, well, this is the way you can tell if A is invertible or not. Do the elimination, see if you get the identity. All right. This is my brief description of the inverse. What can you use the inverse for? You can actually use the inverse to solve a system by multiplying both sides of the formula by an inverse. For example, if I have 2, 1, 3, 2 times some vector of variables equals 5, 2, if that represents a linear system, I can solve the system by using the inverse. We can multiply both sides by the inverse. We can solve for x by multiplying by A inverse, right? I mean, if you didn't know better, you would say, oh, I can solve this for x, just divide by this thing on both sides, and then I'll have x all by itself. Of course, you don't divide by matrices, but you can multiply by the inverse, and that's basically the same thing. So if I multiply on both sides by A inverse, this is the same matrix I was just talking about, so the A inverse for this guy is the same. It's 2 minus 1 minus 3, 2, right? So to solve this, I can just multiply on both sides by that. 2 minus 1 minus 3, 2 times what I had before, 2, 1, 3, 2, x equals 2 minus 1 minus 3, 2 times 5, 2, right? I inserted that A inverse on both sides. But on the left side, those two guys are going to cancel because they are inverses of one another. When you multiply these together, they give you the identity matrix. Identity times x equals that stuff, but identity times x is just x. And then what do I see on the left side, or on the right side? I can actually just multiply those together, right? Doing the matrix multiplication. I get 2 times 5 minus 2, so that's 8. And then on the second row, I get negative 15 plus 4, negative 11. So this is another way you can solve a system by using an inverse. All right. I am running out of time. I had quite a bit more stuff that I want to talk about, but we'll go another 10 minutes. I don't know, how long did you guys expect to go for? An hour or so?
Yeah, an hour's good.
I don't know. Yeah, okay. So we'll see if we can go another 10 minutes and hit a few more things. And then maybe I'll just give you like a list of things that I didn't get to so that you can try and fill in the blanks. I mean, obviously I'm not getting to everything, but I'm trying to give you the highlights. How about determinants? This is an important thing. The determinant. The determinant is a specific number which we write like this. This is, we write it sort of with absolute value signs, even though it's not really related to the absolute value. The determinant of a matrix, and what it is principally useful for is, this is a number, first of all, and it's most useful for telling if a matrix is invertible or not. That's why it's called the determinant, because it determines whether the matrix is invertible or not. A is invertible if and only if the determinant of A is not 0. So if you want to know if a matrix is invertible, this is one way to do it, by finding its determinant. Here's how you find the determinant of a 2 by 2 matrix. There's just a formula that you need to memorize, I suppose. It's simple enough. It is AD minus BC. This is the determinant of a 2 by 2. And for a larger matrix, you have to do a complicated procedure, which we call expansion of the cofactors. Here's an example. This will come back to you, I think. 1, 2, 1, minus 1. All right, this is a 4 by 4 determinant. How do we do this? We choose a row or a column to go across or down, and you multiply what we call the cofactor. So I'm going to do this by going across the top row here. I'm going to go across the first row, and what you do is you take each element in that row and use it as a coefficient, and you put it in front of the subdeterminant. So I begin with a 2 as the first coefficient, and then the 2 is multiplied by a 3 by 3 determinant of what you see if you erased the column and row that that 2 is in. So I multiply that times this 3 by 3 determinant, 1, 2, 5, 1, 2, 1, minus 1, like that. All right? And then I move over, and I do the same thing with the next thing in the top row is a 0. You have to remember to alternate the signs as you do this. So next is minus 0 times, and now the 0, what I look at for the submatrix for the 0 is eliminate the row and column that 0 is in, and I take the 3 by 3 of remaining guys, which will be 0, 2, 5, minus 1, 1, minus 1, 1, 1, minus 1, like that. All right? And then I continue. Next is the 3. So now I go plus 3 as a coefficient, and then the submatrix for that will be 0, 1, 5, minus 1, 1, minus 1, 1, 1, minus 1. And then finally minus 4, and then the submatrix for the 4 is 0, 1, 2, minus 1, 1, minus 1, 1, 1, minus 1. All right. This is... that's the first step, and now you have to do that again with each of these submatrices, which is a real pain and can take you several minutes to carry this computation through all the way. Unless there are a lot of zeros. If there's a lot of zeros in the matrix, then it works out nicely. This one, for instance, we can ignore entirely because it has a 0 coefficient. But the others, we really would have to continue to compute them by doing this same procedure on each of those 3 by 3. So can I just say equals, etc.? It's probably a good idea for you to learn how to push the button on your calculator that finds the determinant. Your calculator can do this fairly easily, so that's another thing you should look into. All right, that's the basics of the determinant. The other important fact that you should know about the determinant is this, also a fact. The determinant of A times B is the determinant of A times the determinant of B. This comes up and is important in a lot of different contexts, but I don't think I want to say much more about it than that's what it is. It's a fact, all right? One thing that sort of forms the backbone of the whole semester in linear algebra is what some books call the invertible matrix theorem. If you know that a certain matrix is invertible, that immediately tells you lots of other things about that matrix. So this is about an n by n matrix. These are all equivalent. So everything that I'm about to write is really another way of saying the same thing. So one is A is invertible. This is equivalent to saying that the determinant of A is not 0, because I just said that determinant A is non-zero if and only if A is invertible. This is also equivalent to saying that A turns into the identity matrix after elimination. But it also means many other things about, say, systems of equations involving A. So another thing it means is that the equation AX equal B has a unique solution. For any B, all right? This is another big important thing. It also means things like the rank. I haven't mentioned this word, but it's an important word. The rank of A. The rank means the number of pivots you get when you do the elimination, or the number of leading ones you get at the end of the elimination. Is n, right? I said A was n by n. The rank is n, means you get a 1 in each of those positions after you do the elimination. That's obvious after, because I already said you have to get the identity matrix. All right. Maybe I'll just leave it at that. There's many other things that you can say about this. All right. If I'm gonna make it an hour, I got 5 more minutes. I'm just looking through my notes, trying to decide what's the most important thing I can say in the remaining 5 minutes. How about I'm going to waste all my 5 minutes trying to choose the perfect thing to say for 5 minutes. Let's talk about vector spaces just a little bit. So most of linear algebra concerns the set of vectors Rn, right? You're doing all of these things in the Euclidean space, Rn. But a vector space, so I'll just say we can do all this in any vector space, not just Rn, right? Rn is a specific example of what a vector space is, but more generally, more abstractly, a vector space is any kind of set in which you can add and do scalar multiplication. And if you recall, you probably learned it like a set of 10 axioms or something, which is very much like what you learned about the group axioms in your abstract algebra class. There are axioms for vector spaces. Vector spaces have 2 operations, the addition and the scalar multiplication, and they have to satisfy a bunch of properties. But anyway, so Rn is a vector space. But there are others also, I would say, like M by n. This is the set of all matrices, of all M by n matrices. These are a vector space. That is, you can add them together, you can multiply them by scalars, and you can do all this, you know, independence, linear combinations, all of that stuff. Also, Pn, this is the set of polynomials of degree n. And in any of these contexts, we can talk about independent, dependent. We can talk about spans of things in the context of matrices or polynomials, not just about vectors. All right. I think maybe I'm at the point where I should just start throwing out a bunch of concepts which I didn't get to talk about in detail, but you should try to look up because I think they're important. So I was also going to discuss, like if I had another hour, I would have talked about, so let me just say, also important, I'm just going to spit out some terminology. Subspaces, right? There are a lot of problems involving sort of, I describe to you a vector space and another thing, and you tell me, is this a subspace of that? Subspace means that it's closed under addition and closed under scalar multiplication. I hope you remember that. Look into some old homework problems about that. I'm sure you can find some from your linear algebra course. Another important concept is, these are in no particular order, the 3 fundamental matrix spaces. They are the row space, the column space, and the null space. You should know what those are and how to find them. If I give you a matrix, tell me what the null space is. Tell me what the column space is, right? The row space is defined to be the span of the rows. The column space is the span of the columns. And the null space is the set of all solutions to Ax equals 0, also known as the kernel. In algebra, you call this the kernel. This is the set of solutions to Ax equals 0. All right. You should also know what it is and how to find a basis for a subspace. A basis consists of vectors which are independent and their span is equal to that subspace. So you should be like, for example, very specifically, if I give you a matrix, I might ask you, find me a basis for the row space, or find me a basis for the column space, or find me a basis for the null space. All of these things can be done by reducing it to the matrix elimination and doing some simple tricks. Another thing I was going to talk about, had I had enough time, was linear transformations. These are functions from one vector space to another. Could be Rn, could be something else. A function t which satisfies these two properties. T of x plus y is t of x plus t of y. And also t of a constant times x is a constant times t of x, right? I hope this looks familiar. These rules are very similar to the rules in abstract algebra for a group homomorphism. Remember that is a function which acts like f of xy equals f of x times f of y, right? In a group, the only operation you have is multiplication, so this is the only way that you could write such a property. But in a vector space, you have addition and scalar multiplication. So these are similar properties for addition and scalar multiplication. If I describe to you a function, you should be able to tell me, is it a linear transformation or not, by checking these two properties. And that also is not really hard to do. You should probably review for yourself how to do it. And what else I got on my list? I think there's only one other thing that I didn't quite get to, and that is eigenvectors, eigenvalues. Very important, but unfortunately, usually we only get to them like in the last few days of the linear algebra course. But they're super useful. I don't know if you came to our latest colloquium talk. Haley and Cameron, they were doing like eigenvectors, eigenvalues all summer long. I gather. I don't actually know, but that's what it sounded like to me. Eigenvectors, eigenvalues are super important. And there's if I give you a matrix, you should be able to find the eigenvectors and the eigenvalues. There's a procedure to do it. It's not terribly hard to do, but there are a bit of, there's sort of a lot of steps you have to just remember how to do it. And I think that's all that I have to say. I got to pick up my kid from her swimming lessons. But is there anything, I don't actually have to leave for another 10 minutes or so. So is there anything briefly I can say about any of this? I'm sorry I didn't get to everything, but you know, you can't really get to everything. Anybody have any questions or comments? All right. I would be happy to you know, talk with any of you. I would say come by my office sometime. But if you send me an email, like if you do have, you know, problems you're working through and you just can't figure them out, I would be happy to go over anything. Send me an email. We can set up. I mean, I can try and help by email, or we can talk by Zoom. All right. All right. I guess that'll do it. Thanks. Thanks for coming. Hope you have a good night.